ready to open up the subsea safety valve. If you open up SSV 16.
Safety valve come back.
Loud and clear. Yeah, go back, Davey.
Go ahead, Fed.
Yeah, I'm looking at 8.5 bar in there.
It's fine, John. Now we've got the subsea safety valve open. If you move on to the lower master valve, FCV 1602. Just crack the choke, Fred.
Yes, John.
Okay. Okay, we're now through the critical zone. We should be flowing into the production header now, Fred.
Okay, I'm getting the pressure going.
Okay, we'll hold the choke steady there, Fred. Yeah. Okay.
The involvement of Amerada Hess in the North Sea dates back to before any oil was discovered. For the first 20 years, the company invested in the North Sea as a non-operator. This early commitment led to the discovery of some 8 oil fields and 2 gas fields. All fields have a production life, and these discoveries were predicted to decline around the late 1980s. So looking to the future, the company decided to purchase a development. Managing Director of Amerada Hess Limited, Sam Laidlaw.
Exploration was obviously one way to do it, but the lead time was so long that we really needed to look at seeing if we could find another development to replace our existing fields which were starting to decline. And that was really the basis for Ivanhoe Rob Roy.
In December 1985, Amerada Hess purchased the UK assets of the Monsanto Petroleum Corporation. These included the valuable Block 1521A with its 2 undeveloped oil and gas fields, Ivanhoe and Rob Roy, located just 3 miles apart.
The first field to be discovered was the Ivanhoe field, which was discovered in 1975, and was a very small field, some estimated at that stage to be something around 30 million barrels, and was clearly in 460 foot of water, not an economic proposition to develop by itself. The interesting thing was that in 1984, the Rob Roy field, which is about 3 miles away from the Ivanhoe field, was discovered, which is about 55 million barrels. And whilst really neither field would be economic by itself, when you aggregate the two, then collectively the economics are sufficiently attractive.
Beneath 460 feet of water and some 8,000 feet of rock lies 105 million barrels of oil and 65 billion cubic feet of gas, which together make up the combined reserves of the 2 fields. The fields are 2 separate faulted structures. The oil and gas are held in reservoir sandstones in the Upper Jurassic Piper Formation. Each field consists of 2 sand formations separated by a continuous layer of shale. In this 3-dimensional model, the thin blue margin at the top of the picture is the sea depth, giving an indication of the scale of the operation. 9 vertical exploration and appraisal wells were drilled over a period of 10 years to define the aerial extent of the 2 fields. Exploration Manager Richard Hardman.
The most notable feature about Ivanhoe and Rob Roy is their very small aerial size. I mean, the perfect offshore field is one that's just small in surface area, but with a very thick oil column, so that you can exploit it with minimum number of platforms.
In fact, the 2 fields would be developed through this floating production facility, moored centrally between them. The vessel would be held on station by a complex 12-point mooring system, capable of withstanding the rigors of a 100-year storm. The connection between the dynamic vessel and the fixed wellheads would be made by flexible risers, which would reach down to the riser base manifold, an underwater junction box which would connect with 2 production manifolds, one on Ivanhoe and the other on Rob Roy. Flexible flow lines would connect each well to a fixed position on the production manifold. A total of 18 subsea development wells would be drilled, 8 on Ivanhoe and 10 on Rob Roy. A computer on board the vessel would control the flow of reservoir fluid from each well to the well head and on to the production manifold. From here, it would be directed via the riser base manifold to the vessel for processing. The economic viability of the concept hinged on the use of a converted vessel to house the production facilities. Vessel conversion engineer Ian Middlehurst.
To convert a vessel takes in fabrication time roughly 6 months to upgrade it to the structural adequacy that we need for the sort of performance we want in our field. Whereas to build a new vessel would take roughly 18 months to 2 years. And in the oil industry, especially, time is money.
This established, the project was set on a fast track to first oil. But in 1986, the oil price fell to an unprecedented $10 a barrel.
We felt that there was a strong chance the prices might go down to $18 or $20 a barrel. I don't think anybody believed the prices would go down to $10 a barrel.
Almost immediately, the company re-evaluated the schedule, and the decision was made to spend an extra year reassessing the engineering of the project. At the same time, the decision on a suitable vessel for conversion was made. Project manager Rex Gaisford.
We made the decision initially between a platform and a floating solution on the grounds of cost and speed. It was then a question of looking at the right vessel to carry out the modification. Now, we looked at quite a few Arca H4 series vessels, and it was very clear to me that we couldn't get a 60,000 barrel a day facility on the back of an H4. So we looked at a flat deck type of vessel, and the 700 series was really the ideal for that purpose. The Phillips SS happened to be available at the time, and it was also quite a good vessel from the point of view that it had never been used as a drilling vessel, so it was actually in very good shape.
Renamed the AH-001, the Phillips SS original role had been as an accommodation and firefighting vessel, mainly in the Norwegian sector. The first job was to strip off all redundant equipment not required for the conversion. The next task would be to ensure that the vessel could remain on station offshore for the field life of 10 to 12 years.
The original vessel had a fatigue life at the critical joints of between a year and 3 years, depending on which joint we chose. And that was not acceptable, as we've got a service life of 10 years minimum, which we want to leave the vessel on the field. So we had to upgrade the structural capability, structural strength of the vessel. The easiest way to do that, rather than to tear the vessel apart and strengthen each individual part of it, was to add to it.
Adding to it would take place beneath the decks and involve transforming the hull structure from a catamaran into a rectangle by the addition of 2 new cross pontoons, shown here in red. By spring 1987, the AH-001 was in Nig Bay and dry docked. Large vessels are no strangers to these deep and placid Scottish waters. The villagers in Cromarty on the opposite shore know the Firth and have reason to welcome this new industry.
It's not the prettiest thing in the world, but it's acceptable to us because it means employment for a local population, a good part of the local population. There is a good deal of pollution in the Firth, not so much from this place, but there's a smelter up there, and then there's a distillery. As a Firth, I don't think there's anywhere in the world can compare with it as far as the depth of water, etc. It's a really first-class harbour of refuge here. That's why that thing is built there, because they can pull the biggest of rigs right straight into deep water. time there were no fish in the Firth as far as we could see, but the fish are coming back now. It's a very, very old port. This goes back, well, almost to Roman times. This place is known as Portus Salutis, right, harbour refuge. Yeah. So it's got a long history.
Almost 2,000 years after the Romans visited these shores, the technology of pontoon construction, something they well understood, is in full swing. The cross pontoons were manufactured on site at Nig Bay, and the internal diameter of each one measures 6.5 meters, just a meter less than the diameter of the Channel Tunnel. Working to the design generated by the project engineers demanded close liaison between the construction site and the Amerada Hess Wimbledon office.
The primary means of liaison with the people on site is through the design drawings, which specify exactly to the thickness and the size of weld every new component that's added to the vessel, every component that's taken away. And those are given to the site team, and they turn those into a steel.
Offshore oil and gas was being flared as the Ivanhoe and Rob Roy development wells were tested. Data from the wells enabled reservoir engineers in the London office to build a mathematical model of the reservoir below. Reservoir engineer David Marshall.
The reservoir simulator is a mathematical model which actually models the field inside the computer. The information we collect from the development wells is put in there, things like structure, fluid properties, rock properties, and we can start the computer running and it will take us through the production history of the field. This lets us try out varying development scenarios without actually producing a barrel of oil to surface.
While analysis of the future production output continued, rollout of the cross pontoons started. It's early July 1987. The first pontoon begins its journey. $550 tons of precision-built structural steel and piping crawls slowly down the slopes of the dry dock towards the AH-001. The rollout, a milestone event, reflected the efforts and dedication not just on-site, but of the Amerada Hess project team behind the scenes.
Very low, so we just wait on your further
until
instructions.
we get the final.
We are interested in doing this work.
We tried to keep it front-loaded so that hopefully there was a wee bit of float at the back end.
The next milestone will be the flooding of the dry dock. First, the hull must be completed, but already planning is underway for the flotation of the AH-001.
What we are saying is that the things we have to succeed with are becoming fewer.
We want a pump room cleared, freed, a no-go area, then that's the ideal situation.
We need to provide you with the condition in which the pump room needs to be for the work that has to be carried out, and the period programme, in effect, for us to carry out the work that we're responsible for and for you to carry out the work that you're responsible for in that pump room in the support of those activities. Then we've all got a working picture and we can decide when it's going to be achieved. And that then determines when the dock can be flooded.
On the misty Scottish night of the 19th of October 1987, a time-lapse camera records the 21 hours it takes to fill the dry dock and refloat the AH-001. She is now a fully fledged vessel. Her first journey is a 4-day trip to Tyneside. Conversion of the hull had been a massively complex task, pushing the skills and the computers of the team to their limit. But the fundamentals of the work are based on well-tried marine engineering techniques.
The main difference between oil rigs and a ship is that most of the structure of a ship is to keep the water out. Now, oil rigs, they're really an extension of the sort of pier that you'll see at Southend. Latticework structures, far less steel in it, and all that steel is doing is acting as a structure, so that its prime purpose is to withstand the load. Now, when we get into a semi-submersible, it's a little bit of cross between the two. We have the pontoons and the columns, which are essentially ship-like structures to keep the water out. And then connecting the two, we have the offshore oil structural element, which is the bracing system, which is taking the loads. The whole technology of structural engineering is developed so that all the rules which we work to, all the standards which we set, have got a margin of safety in them to allow for the uncertainty in design and material, because each one is a prototype. Each one is different to the others.
As the AH-001 slipped into the Tyne, the birthplace of so many ships, it made history as the largest vessel ever to sail the river. By this stage, 4,500 tons of redundant materials had been removed from the empty decks. Decks the size of Wembley football pitch, now lying ready for the installation of the topsides production facilities at McNulty Quay. In Wimbledon, the construction of a scale model of the topsides is well underway and gives a clear view of the task ahead for McNulty Quay. Even at small scale, it's an enormous model. Its job will be to verify the position of every component and untangle any problems before full-scale construction.
Get upset if I take it out.
Seen from above, these look like models too. In fact, they're the 3 massive subsea manifolds at Hartlepool, where they were fabricated over a period of 11 months. Rex Gaisford.
Well, the whole project is based on underwater technology. The manifolds themselves contain basically 2 items: hydraulically operated valves and electro-hydraulic pods. And these pods accept electronic signals from the vessels, convert them into hydraulic signals, and the hydraulic signals actually operate the valves. The valves themselves are very carefully made and very expensive and have to be maintenance-free. The electro-hydraulic modules are very sophisticated animals, and of course they have to be capable of running electrically in 470 feet of water.
For instance, in this case, over on there, again with its position.
With the delivery of this Christmas tree and the subsea control system, both assembled in Aberdeen, the string test at Hartlepool can begin. Mechanical piping engineer Mike Hillier.
to a certain extent, each of these items have been both designed and built in separation. Theoretically, on paper, you connect them all together, they work. They've all been individually tested, the computer at its manufacturing plant, the software in the software house, the manifolds here on site, all the various subcomponents. A string test is the one opportunity to actually physically hook everything up and verify that all the various interfaces actually work.
This string test is the final dress rehearsal for every part in the show.
Well, you step in a choke 2 degrees open from 83 to 85 degrees.
A show that will take place in about 500 feet of water.
Reading 85.
A show where no single part can be allowed to fail.
Choke is now reading 85 degrees. That's it.
And everything you see here, sooner or later ends up under 500 feet of water. And it's only when the vessel gets on location for the first time and the last connection is made, you have the opportunity to repeat, in fact, the string test that we're doing.
Each manifold weighs around 350 tons, and despite their size, each is a piece of precision engineering that must be handled delicately. From the barge, the riser base manifold was transferred to a heavy lift vessel to be prepared for its one-way journey to the seabed. With the weather set fair and the schedule pressing, work on deck will continue throughout the night.
There's been an agreement on the beach that we may use yourself for the diving as a last resort if things don't go quite as planned with the Smith Semi. But it just may be that we require you for diving tomorrow, but that's sort of a little bit into the background now.
The morning of May the 14th, 1988, broke to a beautiful blue sky and calm sea. By the time Sam Laidlaw and Rex Gaisford arrive, the Dutch installation engineers have the manifold ready to lower.
As soon as we have it in position, then we hand it over to Smith. Then we put it in the right position, and then, well, the divers do the rest. Die kaarsen krijgen later. Ja, oké, we houden steeds een beetje stil.
The successful installation of the riser base manifold marked the beginning of the busy 1988 summer offshore construction period.
This time a year ago, we'd only just started on the cross-hull pontoons of the vessel, and we hadn't done any of the offshore installation, and this really is the first major milestone for the offshore installation, the installation of the riser base manifold. Shortly later in the summer, we're going to be putting in the 2 production manifolds and, of course, tying them all together with the subsea flow lines and piling them all in. And that really is the major program for the whole of the summer.
The project's absolutely on schedule at the moment. It's had its little ups and downs, but we're still going exactly according to plan. And all the subsea work for 1988 is going to be finished in '88.
The optimism that followed the successful installation of all 3 manifolds is now focused on Aberdeen, where a new shore base will be opened.
When we started, of course, Ivanhoe Rob Roy, the Aberdeen community, I think, was going through a fairly difficult time with the general rationalisation that not only the oil industry, but a lot of related supplies industries were undergoing at the time. I'm pleased to say that actually that Aberdeen is relatively buoyant once again, and I think that in a small way we've played a contribution to that.
Good afternoon, Amerada Hess. Can I help you? Certainly, sir.
In July 1988, the offices, integrated pipe yard and warehouse of the new shore base were opened in Aberdeen.
Bring her in backwards so that we can...
Prior to this, the Aberdeen operation had been handled by a small team responsible for the company's exploration drilling. Now the task was to recruit and build up an operations, production and maintenance team to run Ivanhoe Rob Roy directly from this new, much larger Aberdeen base.
We had an enormous number of applications for the Ivanhoe Rob Roy project and for the Ivanhoe Rob Roy operations. For the operations alone, I think we had in excess of 4,000 or 5,000 applications. So it took a lot of processing, but we, in fact, I think did, as a result, get very high quality.
The quality of life at the Aberdeen shore base is just another example of the company's commitment to people. A commitment reflected in its team spirit throughout the company, whether working offshore or at the annual sports day.
Ready, steady, go!
Got one.
Of course, this commitment to quality is at its most crucial in the design and construction of the topsides at McNulty Quay. By now, processing equipment was arriving on site from all over Britain and Europe. The total UK content of this project was to amount to over 85%, reflecting the company's sourcing policy.
We haven't, in fact, been maximising UK content through a sense of obligation, but through a sense of actually believing that they can do the best job. And the response we've had at a difficult time in the industry has been outstanding.
In February 1988, a Dutch heavy lift vessel lowered the first large item of plant onto the decks. The de-aerator tower was built in Gloucester and weighs 53 tons.
Nog zo'n stukje, Herman.
Positioning of the tower is critical for the stability of the vessel, and welded posts are used to guide it into place.
Just a hot turn. Oh, the website is here. Yeah, yeah. Alles goed.
Over 18 months, as the decks gradually became crowded with the processing equipment, the role of the scale model became crucial, enabling the project engineers to visualize problems in 3D.
Hold on for this side, but we do need a takeoff on the airline.
Well, we've got a 3-inch there. We can tee off and bring it through here.
Offshore, this complex labyrinth of steel and pipework will be dedicated to a specific task. That task, to safely and efficiently extract oil at the rate of 50,000 barrels a day. This process would involve the separation of water and gases from the crude oil. Inside the separator, the reservoir fluid will be propelled into the tank and turned into a spray. The oil, seen here as green, and water, as blue, will settle out by gravity, and the gases, represented in pink, will remain in continual motion at the top of the tank. The gases will be compressed. Some will be used for fueling the gas turbine generators which provide electrical power on board the vessel. Small amounts of impure gas will be flared off on the cantilever flare boom. Some gas will be used to help lift the reservoir fluid. But most of the gas will be exported by pipeline to Scotland via Tartan, the first time this has been done from a floating production facility. Crude oil will travel to Flotter in the Orkney Isles via the Claymore field. Offshore, these pipes were laid in the well-tried fashion. This pipe-lay barge laid the pipe at the rate of around 4 kilometers a day, followed by a ploughing vessel that safely buries the pipe in the seabed. The third product from the separator is produced water, and its treatment before entry into the marine environment is of paramount importance. Safety engineer Gordon Rayburn.
If you treat the waters with chemicals to try and separate the oils out, some of the chemicals themselves are not particularly good for the environment, and you may get carryover and they may end up in the sea as well. So it's better to try and use mechanical methods to separate the oil from the water.
The installation of these hydrocyclones will provide that mechanical rather than chemical solution. Water from the separation process still contains some oil residue. This oily cocktail will pass into the hydrocyclone, where it'll be swirled vigorously by centrifugal force. And the oil, seen here as green, being lighter, will migrate to the core of the fluid and will be drawn off. Polished to less than 40 parts per million, the water is now sufficiently clean to be piped into the sea. Technical manager Mike Unstead.
We do perhaps go rather more than some companies in observing all the environmental rules, and we in fact often move first, doing rather more than is required. Certainly we will adhere to all the existing legislation in order to make sure that we do not make the situation worse than when we inherit that piece of the ocean.
Among the other innovations, this seawater pump is entirely self-lubricating and represents both a weight and cost saving. The white-clad Ruston gas turbine generators are a new type never before used offshore. In parallel to the topsides construction, another target was to commission the vessel as fully as possible by the sail-away date.
On this job, the intention was to go out from the inshore site with the vessel fully commissioned. So as soon as systems became available from the constructor, then our commissioning engineers and commissioning technicians got in, took over control of those individual systems and started to do commissioning work, ending up finally with live commissioning of the plant.
8 to 10 days' time for actual energisation and requiring the first hot work permit.
No matter how safely you design a project, unless you actually have the operating staff properly trained and constantly aware and vigilant, then you'll not have a safe operation.
As the AH-001 was fine-tuned for its task in the North Sea, the men who would man her were rigorously trained in offshore survival.
You're rotating 180 degrees very quickly then, so breathe out very sharply from your nose, and that will compensate for it. It'll snap. It's released.
It makes you feel confident in the fact that if an accident does happen, you're aware of procedures how to escape from helicopters.
We have records of what training our people have and what training they should have. And as far as our contractors are concerned, we monitor that as well and make this same training a contractual obligation.
Suddenly, safety was highlighted worldwide. On the morning of the 7th of July, 1988, the Piper catastrophe sent shockwaves throughout the industry. By then, the AH-001 was 80% complete. Nevertheless, the company embarked on a further safety program. Rex Gaisford.
We brought in a specialist consultant to carry out hazard analysis and risk analysis on the platform. And as a result of that, we did some quite considerable modifications.
These modifications were to result in a further £15 million being spent. Extra protection for sensitive processing equipment on the decks and pyrocrete lagging at the base of this flare boom were installed. Blast walls around the turbine generators provide protection for the rest of the deck, while an extra coating on the helideck and accommodation unit will give protection from a 2-hour hydrocarbon fire. A new walkway and secondary deluge system provide an alternative underdeck means of escape. Offshore, subsea installation could proceed as planned. This white coil of pipe is one of the crucial flexible risers. It was laid ready for the AH001 during April 1989. The flexible risers are without doubt the most innovative element in the entire Ivanhoe Rob Roy project. Sam Laidlaw.
The flexible riser system, the configuration that we've got, is certainly unique, and we'll certainly be the first people to be exporting gas using a flexible riser system.
Back at McNulty Quay, work continued 7 days a week, 24 hours a day, to meet the sail-away date. And by April 1989, the vessel, a complete working and living environment, stood ready for action. On the afternoon tide and with little ceremony, the AH001 slipped berth and sailed majestically down the Tyne, bidding the skills and dedication of the Tynesiders farewell.
We were able to sail out to the field in a condition that we could operate straight away. The fire pumps were running, the accommodation was fully working, the caterers were on board cooking dinners, and all aspects of utilities, main power and so forth, were all running.
Arriving in the field in such good shape enabled final hookup of the AH001 to the flexible riser system to be completed in just 2 months. With every complex connection between the static subsea equipment and the dynamic floating production facility fully commissioned, first oil flowed. Amerada Hess became a producer in the North Sea for the first time.
Well, I think the exciting thing about Ivanhoe, Rob Roy, is it really provides an opportunity for growth.
It has given us an opportunity as a company to demonstrate our capability in the operating field.
We've got a major operation on our hands from a production point of view. We've got a new, even larger project to build from a development point of view. The company's confidence has gone up enormously in that period of time, and it shows, I think, in all forms every day.
The main export area, connecting via the high-level pipework.
Our non-operated acreage is always important, and we see developments there. And of course, we've got very recently new blocks in the 11th licensing round too, so we'll also be doing more grassroots exploration.
We're in the second generation of exploration now, and we have to use much more thought. In the old days, it was just drilling on the upturned bucket, and now we're drilling down the side of the upturned bucket to see what's trapped there. It's a very much more subtle game. It's much more manpower intensive, and thankfully, we've got a lot more technology that we can bring to bear on this problem.
In fact, it's a fairly optimistic picture all round. Oil prices have also seemed to have stabilized for the time being at acceptable rates, and I think the future is a good one.